Okay, hello everyone. It's nice to see you in person. Because it has been a while. This is Advanced Systems and Controls, so more power to all of us. Let's pick up where we left off last time, which was we were talking about a review of systems and controls. And one of the things that we talked about last lecture that was kind of an important piece is the idea that we can actually take transfer functions and we have the ability to change those transfer functions according to how we want them to be. Okay, before I get there, anybody remember how to calculate a transfer function?
Output over input.
That's all it is. A transfer function, the definition of the transfer function is the output over the input. Now, it doesn't always have to be put the output in terms of time over the input in terms of time. That really only creates a linear function if it's in the time coordinates. Put it in the s coordinates, it becomes much more able to become a linear function. But we take this concept and we basically say, okay, well, if you can come up with some function of the input is equal to some function of the output, this is still a solvable problem, okay? While we can't, we may not necessarily be able to nicely get it in terms of output over input. We can take this concept here and we can use this to create a relationship between what the output and the input is. And this gives us the ability to really modify how things work. So in terms of systems and controls, this is kind of one of the most critical pieces. Solving these functions relative to each other, you can do it with Python. And it's a process, but it is doable. But at the same time, not a lot of people are sitting down and solving these equations in the real world, if we're honest. Usually you go for an approximation that's close enough. And for that, we talked about what happens when you measure and you get some kind of a line that looks like this, and here, this is your input, and this is your output. And then you develop a regression line that most closely matches this. You try to get your R squared value really close to 1. Or maybe you get it at 0.9. And then you can take this relationship that you develop and say, well, this is good enough. Because if we take this good enough, while yes, it doesn't exactly give us this, it does give us a close approximation for what's going to happen when we change this input. Okay? Another thing that I mentioned on the lecture on Wednesday is what happens when you get to do parametric equations. And I did not want to try to explain that over over YouTube. Does anybody know what the term parametric means? Yeah. Yeah, it's something where it has a much more complex shape than just a Cartesian coordinate. So we're used to the Cartesian y of x is equal to x squared plus 4 or something like that. This is Cartesian because y can be put directly in terms of x. In parametric equations, what you have is you have a function y of t is equal to t squared plus 4, but then you also have x of t is equal to t plus 3 sine t or something like that. okay? And this is the big difference between what we're used to in more Cartesian settings versus parametric. In parametric, what you have is both your input and your output values are actually functions of time. And that makes things a lot more challenging because then you don't get this nice, neat relationship where you have one function on one side is equal to one function on another side. You would have to try to solve both of these functions for t in order to try to make this happen. So one of the big issues that you have when you start looking into more complex mathematical systems is that this now suddenly becomes much more of a challenge. Now that said, this method here, where you plot them relative to each other, you say, it only works between this bound and this bound, that actually still works. And you can do that no matter whether or not it's parametric or whether it's Cartesian. We're basically trying to model a Cartesian system given whatever inputs you have. So this is something where statistics really comes in handy, and I don't even think I stated statistics as one of the potential prerequisites for this course. But if you've taken statistics, understanding systems and controls actually does make it easier, because now instead of just having to only do it this way, you can now actually take measurements, real measurements, and apply systems like that. Come up with statistical models, develop equations on your own, come up with good fits, try to increase your fit once you find a better fit, that type of system. Okay. So, is there any questions that you have on transfer functions as far as, is anybody who didn't understand that well in 350 or wants more discussion on that? I could talk about this all day. Hearing none, we'll move on. So one of the other really important concepts of 350 is not just the transfer function, which, yes, transfer functions are really important, but it's also the concept that we're working with systems. When it comes to working with systems, the piece about systems that makes them so critical is that every component in a system contributes to the overall behavior of the system in some way. If it doesn't contribute, well, then it's not an essential feature. Okay, so as we talk about this, every component in the system contributes in some way. If we had a gear train, and pardon me, I'm about to really poorly draw a gear train. Okay, if we have a gear train in here, maybe this gear is being driven by, I don't know, a motor with a very small, I don't know, something. Actually, I'm going to draw it over here. We have a very small gear that is driving this. Maybe this is attached to a motor or something. If we have this gear driving this gear train, what you'll notice is that the amount of power that the input has to put in is dependent on how many gears are outputting power. Okay, the more gears you put in there, the more friction is going to exist. The more gears you put in there, the more outputs you have potentially. You may have this gear driving one function. This may be driving a refrigeration cycle. This may be driving a timing belt, something. Okay, you have all of these contributing to something, and what that means is this has to put in more power in order to satisfy the rest of your system, and then this is outputting power, this is outputting that power, this is outputting power, but this has to carry the power that's being used here, which has to carry the power that's being used there. So it really becomes an issue where every one of the components in your system is contributing in some way to the overall system behavior, to the overall why forces are transferred in the system the way that it is. So this does make systems more complex to evaluate. Now, with the concept of the transfer function, we can just very simply say, well, I'm going to take an output, I'm going to measure my output, and then I'm going to measure my input, and then I'm going to come up with some kind of a relationship between the two, okay? I'm going to bypass all the math. I'm just going to very empirically derive what this relationship is by measuring both of them and seeing what the relationship is, okay? You can do that. You can do that all day long. This will give you probably the closest to the most accurate interpretation of what the relationship between both of these are, which will then allow you to understand what the output behavior is based on what you're doing for your input. You know, you put in X amount of power, you get out X amount of power out here, okay? So that's one way of doing it. The other way of doing it is actually to figure out what the relationship is that steps in between each of these. So empirically measured, here this kind of ignores, it basically treats it like a black box, and it just says here we have some kind of an input, it goes into some kind of a system, and then it develops an output, and I don't care what's in that box. All I care about is that I can empirically measure what the relationship between these are, okay? And that's how you basically develop your transfer function. When it comes to complex systems, this can be nice because, quite frankly, then you don't need to do any math. You know, your math falls into only doing statistics, only graphing, only taking measurements, okay? It makes it much more simple, but it also makes it much more challenging because now the pieces that you may be ignoring are how do other inputs, how do other errors affect the actual performance of the system, okay? So if you simply try to measure a system and say, okay, well, this is all it is, well, it doesn't take into account the fact that this one may be connected to a belt. If that one's connected to a belt, then the output power from that gear might be changing. And if the output power from that gear is changing, it is going to change how much torque is being transmitted through this gear. If you change how much torque is being transmitted through this gear, that's going to be able to change how much friction this gear is experiencing. And so it does make the whole system more complex, and it also means that if you're measuring the way that you measure your transfer function, if the conditions are not identical to the conditions when you measured that transfer function, it's now completely wrong. There's nothing right about it. It might give you a ballpark idea, but it might also give you false ideas of what that transfer function actually is. So coming into the discussion on systems versus just simply components, you do have to have some kind of an understanding of how to, component by component, create a basically create the relationship that guides how power is transferring through the system. So when it comes to talking about power transfer, what we're really talking about here between components is we're really talking about physical relationships. This is physical principles by which power is transferred. Okay, so you basically have to have a really strong understanding of physics if you really want to understand everything here. Now more than likely, if you're working with a very specific system, you can go figure out, okay, you know, when it comes to rotational systems, you have torque and you have angular rotation, and the relationship between torque and angular rotation changes. You can go look up stuff on very specific materials on gears. You can look at very specific materials on belts. That's really helpful, but if you have to do this absolutely every time you try to develop a systems and controls analysis of a system, it can get a little tedious. It's nice to know it beforehand, but in reality, having a very strong understanding of physics is important. Now, the kinds of power transfer that you can be dealing with, I'm going to go ahead and jump up here. You can be dealing with a linear power translation. This is more of a linear system. In a linear system, what you're dealing with is a displacement and a force. Okay? If you multiply force times displacement, you get work. The energy, the derivative of energy is power. So, if you multiply the velocity by the force, you can directly measure the power there. Okay? So any system where you're dealing with this, you just got to remember that it's a displacement system, it's a force system. If it moves in any kind of linear direction and if it experiences force in any kind of way that is measurable, you might be dealing with a linear system. Similarly, we have a rotational system. Rotational power is a product of angular displacement and torque. Now, angular velocity multiplied by torque actually generates your rotational power. That's something that you got to keep in mind. But you also have pneumatic systems. In a pneumatic system, you have volumetric flow rate, and you have pressure. If you multiply those two by each other, you get power. This is a pneumatic system that also has the same principles as a hydraulic system. Again, they fall to volumetric flow rate and pressure. In a pneumatic system, you tend to deal with a higher volumetric flow rate because the compressible gases, they play more of a role, whereas in a hydraulic system, you assume the hydraulic fluid is incompressible. Therefore, you're dealing more with higher pressure systems, usually without nearly as much volumetric flow rate. You deal with electric systems. The electric systems are probably the one that we've talked about the most. This is where you're dealing with voltage and current. Remember, voltage multiplied by current is equal to your power there. We can also deal with thermal systems. And here, thermal systems, usually the power transfer actually just is a rate of change of heat. Okay, and then, any other type of energy system that we have in reality, you can also identify, take the derivative of the energy value there with time, and that gives you ultimately a source of power. This could be anything from chemical. You could even have nuclear energy, which generates heat. You can have solar and electromagnetic radiation energy, etc. Okay? So if you take the time derivative of all of those energy values, that's how you get power. Okay? And power is a principle that is transferable. Okay? I may not be. Yep, I totally started drawing off the screen. That's work me. I'm just gonna do that and then erase over here. Now the nice piece about this is that engineers who have long preceded you have come up with ways to transfer each one of these to each other. Okay? I mean, even if you look at electromagnetic radiation, we have solar panels. Okay, it goes off of solar panels, abide by the black body radiation principle, which is if you hit a black body with electromagnetic radiation, it causes electricity to move. So it's something where all of these physical principles have already been studied, and we've actually developed technology out of them that allow us to transfer. Okay, so okay, so really we're sitting at a kind of a pinnacle of technology right now where power transfer between different types of power is possible. Okay, if you have a lever system and this lever system is attached to a spring or something, okay, and this lever system, as it moves up and down, you are transferring what can be a linear system into a rotational system. As this lever rotates about a pin joint, you're converting a linear movement into a rotational movement. You can change this to being I don't know, some kind of you could be using a rotational potentiometer there to measure how far it's rotating. So we have had the ability to transfer all of these, for a very long time. This is a very simple system. But then you get into pneumatic and hydraulic systems here. You want to talk about moving a linear system and then converting it into hydraulic power. That's what a piston does. Okay, in a piston, the pressure and the volume of that piston changes as the piston head moves up and down inside of the piston. Okay, it's a very simple system. Hydraulic power moves the same way. You've got hydraulic actuators that operate on the principle that they change the amount of material inside of here. It causes the pressure to change, and it forces this to go up and down, extend or contract accordingly. Okay. We've also developed methods of converting linear into electric power. It actually looks a whole lot like a hydraulic actuator. It's basically got a cylinder that looks like this. Inside of here, there are a bunch of magnetic coils where the magnetic coils will experience some kind of an electric field that forces the components to move one direction or the other. Turns it into a linear actuator. We have these things. Okay, you can buy these online. And really we can go through this list and pick any two of these and be like, all right, I'm going to take this one and this one, or I'm going to take this one and this one, and I'm going to be able to try to develop some power relationship out of those two. I'm going to find some technology that converts these two to each other. Okay. So what does that mean for you as the engineer? Well, it means whatever system you're working with, you have a way to get whatever kind of power you need out of it. Okay? So if you're dealing with a thermal system, something that generates heat, but you really need linear displacement, there is a component that has been developed that transfers power from here to here. Okay? They already exist. That's our technology. But not all of them do it efficiently, which is why some engineers are like, well, it's just easier to convert pneumatic power into electric power and then convert electric power into linear or rotational power. So sometimes that happens. Although there are hydraulic rotary motors I've never actually seen one, but I know they exist.
So why is it harder to like convert one energy to another energy than it is like another?
Sometimes the technology that's developed for it is more efficient than another type. Like here, if the efficiency of converting this into this is only 80%, but the efficiency of converting this into this and then this into this is, 90%, you can save energy that way. So
I imagine it's easier to turn something like linear into rotational than pneumatic into thermal.
much, much easier. Although if you're using chemical power does not transfer well into most of these. It transfers well into linear, and it transfers well into pneumatic power because you can blow stuff up. And if you blow stuff up, then it converts into this. So if you're trying to use a chemical into electric, right now that's kind of the relationship that we have to go through. So it just depends on what the system is that you're trying to do. If you can directly convert chemical energy into electric energy, that's called a fuel cell. Fuel cells are still under very, 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 very expensive review and development because they really want to be able to just directly make that power transfer. But it's still an emerging area of technology, unfortunately.
Transferring the power is different than transferring the energy, though, right? All energy goes to thermal.
Well, energy, transferring power is the same as transferring energy because power is just a rate of change of energy. So the way that you transfer that energy, the transfer implies that the energy itself is changing or changing forms. Eventually, yeah, it does all end up in thermal, but it takes some other form before it reaches there, and that's where we're talking about energy transfer. Okay, anyways, the piece that's really nice about this is that we can work in whatever system we want to. Okay? This has had some major implications for society because when we can say whatever system we want to, it means we can make everything be an electric system. Okay? One of the big, if you go on any college campus, there is always a stare down between mechanical engineers and electrical engineers because mechanical engineers say, well, every system can be mechanical, which is true. You can make every system be one of these two, although this falls into mechanical engineering as well. Whereas an electrical engineer says, well, you can make every system be this because you can convert from electric energy to anything else. It really comes down to this principle. Because we have the ability to convert between systems, you can work in an all-electric system. Now, there are benefits of working in an all-electric system as opposed to trying to work in an all-pneumatic system. The HVAC system for this building is all pneumatic, and it is the worst ever. I don't know who thought that was a good idea 20 years ago, but they don't do that. No one does that, okay? Electrically actuated vents are just more effective, more reliable, but nope, they wanted pneumatically actuated vents. So it all depends on whatever system you want to work in, I suppose. Why would people want to work in an electric system as opposed to working in all of these other types of systems, though? What's the benefit of an electric system?